In this last section in Chapter 9, we're going to learn how to calculate the confidence interval for a difference in two means. Now, this is what we'll use when we have situations where we are interested in comparing an athlete's ability in two different contexts where we're using numerical variables. For example, does a basketball team score more points on average at home than on the road? We can calculate the average number of points they score at home and the average number of points on the road, and then we want to find the difference between those two values. And so to do that, we're going to calculate a confidence interval for the difference of two means. Now, this is the formula that we had in section 9.3 when we calculated a confidence interval for one mean. And you don't need to write this in your notes, but I just wanted to remind you of some of the symbols that we used in that formula. Now, with means, our single value estimate is given by this symbol right here, X bar. And since in this section we're going to be working with two different means, we're going to use subscripts to denote the mean in two different contexts. We also need S, and S is the standard deviation. So again, you'll see a standard deviation in two different contexts. And then N is your sample size or the number of attempts. Again, we'll use subscripts there to denote two different contexts. Now, because of some algebraic properties with square roots in the denominators, the formula isn't going to look quite like this. So it's going to look a little bit different. You're not going to see a square root in the denominator, but again, that's just an algebra thing. And if you want to know more about that, you can check with your teacher, or you can look that up online if you want to know how we simplified that algebraically. But anyway, let's write down the formula. So we're trying to estimate a true difference in means. So the value we're trying to estimate here is mu A minus mu B. Remember, mu represents the unknown athlete's ability, and then the subscript A is in one context, subscript B represents the other. So this is what the formula looks like. Okay, we're going to start off with X bar A minus X bar B. So instead of just having one X bar, we have X bar or a mean in two different contexts. So that's our single value estimate. Then we do plus or minus 2, just like we do in every formula. And then this is what it looks like under the square root. Be careful when you're copying this formula down. This A down here is a subscript. That means the standard deviation in context A. This 2 up here is a power. So it's the standard deviation squared in context A. And then we divide that by NA, and then we do the same thing for context B. So let's define our variables. Mu A and mu B represent the athlete's true mean or their ability in each context. X bar A and X bar B represent their observed mean or their performance in each context. SA and SB represent their standard deviations of their performances in each context. NA and NB represent the number of attempts in each context. All right, let's try an example. Can pitchers throw faster when using baseballs with synthetic covers than when using baseballs with leather covers? A Major League Baseball pitcher takes part in an experiment in which he throws 30 baseballs of each type in a randomly assigned order. For baseballs with a synthetic cover, the average pitch speed is 87.2 miles per hour with a standard deviation of 2.1. For baseballs with a leather cover, the average pitch speed is 84.3 miles per hour with a standard deviation of 1.8 miles per hour. Question A is asking us how much faster were pitches with the synthetic covers than with leather covers. So we're going to calculate a difference. Again, just to kind of reinforce the symbol notation, I'm going to do X bar sub S. So that is synthetic. X bar is the mean, right? So the mean for the synthetic pitches were 87.2 miles per hour. The mean for the leather covered balls were 84.3 miles per hour. And so the difference there is 2.9 miles per hour. So that's a pretty good difference, I think. I don't pitch in baseball, but I would think 2.9 miles per hour would be a good advantage for a pitcher. But we're going to use that then to calculate the true mean difference between pitching with those two different types of balls. So we're going to calculate our 95% confidence interval for the true difference in pitch speed, synthetic versus leather. All right, so first we take our single value estimate, the 87.2 minus the 84.3. So that's X bar 1 minus X bar 2, or A and B, or synthetic and leather, whichever subscripts you use. plus or minus 2. And then underneath the square root, we do the standard deviation squared over the number of attempts. And remember, this pitcher had 30 attempts with each type of ball. And then we do plus 1.8 squared divided by 30. Again, with your scientific calculator, you can type all of this in one step, hit enter and store that number in your calculator, then take the square root, store that in your calculator, then multiply by 2. And at that point, then you can round. So we get a difference of 2.9 miles per hour plus or minus a margin of error of 1.01. Now that interval works out to be 1.89 to 3.91 miles per hour. If we interpret the interval, we would say we are 95% confident that the true difference in the pitch speeds, synthetic minus leather, is between 1.89 and 3.91 miles per hour. And just like we did in section 9.3, you want to be sure to include units when you're stating your confidence interval. Because just saying 1.89 or 3.91 could be kilometers per hour, miles per hour. It's really important to include units there. That's just part of the context. And also notice that I indicated the direction that I'm subtracting, right? So synthetic minus leather, the direction is important because my entire interval is positive in this case. So that means I'm getting good evidence that the pitches with the synthetic covering are going to always be faster than leather, or at least almost always, because my entire interval is positive. Let's look at another example. In modern NFL, the passing game rules, but has this always been the case? So we're going to look for an estimate of true passing ability for teams from 1979 to 2009 and see if there's a difference between them. And we're going to use the mean number of passing yards per game for every team in the league. In 2009, the mean passing performance for the 32 teams in the league was 218.5 yards with a standard deviation of 44.1 yards. In 1979, however, there were only 28 teams in the league, and the mean passing performance was 180 yards with a standard deviation of 35.7 yards. Part A is asking you to jump right to the 95% confidence interval for the difference in mean passing yards, and they want you to do 2009 minus 1979. I would recommend that you pause the video and try the calculation and at least see if you can get the numbers plugged in the right spot and see how you're doing with the formula. Okay, here's what the formula looks like with all the numbers substituted in. Remember, we're doing 2009 minus 1979. So when I plug those numbers in here, that order is important. So you want to be sure you get those in the right order. Okay, that gives us then a margin of error of about 20.6 yards per game. And our interval then is 17.5 to 58.7. Does this interval provide convincing evidence that teams in 2009 have a greater passing ability than they did in 1979? Well, again, notice that our entire interval there is positive. So that does indicate that there is definitely a difference. And we're pretty confident that the difference is that they pass somewhere between 17 and 58 more yards per game in 2009 than they did in 1979. So we would say yes, because the entire interval is positive. So all plausible values indicate that teams pass more in 2009 than in 1979. Please do homework 9.5 in your assignment packet.